All right, welcome. We're about to dive into your first real look at the world of engineering. We're going to explore the single most foundational skill you'll need to master in this course, the art and, really, the science of engineering drawings.
Seriously, this one idea right here, it's the key to absolutely everything. We're not just talking about lines on a page. This is a language. It's how we communicate incredibly complex ideas with pinpoint precision, turning what's in our heads into reality, anywhere on the planet.
So check this out. This isn't just some cool picture. It's a complete set of instructions. Every single line, number, and symbol here tells a skilled manufacturer exactly how to build this entire electrical coil winder, from the tiniest screw to the main frame itself.
Yeah, I get it. Looking at something this complex for the first time, it can be a little intimidating, right? It's kind of like being handed a movie script in a language you've never even seen before. But hey, don't worry. Every single engineer starts right here, and we're going to break it all down step by step.
So, before we dive into the ABCs and the grammar of this language, let's just take a second to understand why it's so incredibly critical in the world we live in today. Just think about it for a second. The International Space Station, right? Its parts were built by teams in the US, Russia, Japan, Europe, Canada, all over the world. How did they all fit together perfectly, up in orbit? Because they all spoke this one universal language. It's how a smartphone designed in California can be built with parts made on 3 different continents. This whole system prevents hugely expensive mistakes, and honestly, it's what makes global teamwork even possible.
Okay, let's move on and see how this all comes together. We're going to zoom back in on that coil winder drawing from a minute ago. We're basically going to perform an autopsy on it to understand its basic structure, its anatomy. So any proper engineering drawing has these key parts. You've got these really detailed views of each individual piece with all their measurements. Then you've got what's called an exploded view, which shows how they all fit together like a puzzle. And finally, you have these super important technical notes, like what units we're using and the projection method. And don't worry, we'll get to what that means in a bit.
All right, let's start decoding this thing. And just like with any language, you gotta start with the alphabet, the common abbreviations and symbols you're gonna see on pretty much every single drawing you ever look at.
First up, we've got CSK. That stands for countersunk. It's a super common note that basically tells the manufacturer, hey, I need you to cut a cone-shaped hole here so that the screw head can sit perfectly flat with the surface. And here's exactly what that looks like. See how clean that is? There's no screw head sticking out, ready to snag on something. It creates this perfectly smooth, seamless surface, and that entire specific instruction is communicated with just 3 little letters, CSK. Pretty cool, huh? Next on the list is CHAM, which is short for chamfered. This is another one of those simple but really vital instructions. It's basically an order to take a sharp 90-degree edge and knock it down, replacing it with a nice, sloped edge. This has all sorts of benefits for both function and safety.
So on the left, you see that sharp, kind of risky corner. But on the right, after the CHAM instruction has been followed, you get this clean, angled surface. This can make parts way easier to assemble, it makes them less likely to get chipped, and safer to handle. All of that from one little word.
And for our last letter today, let's look at PCD, or pitch circle diameter. This one is absolutely mission critical anytime you have parts that need to be bolted together, like the wheel on your car or a big cover on a pipe flange.
So what this one little note is telling you is, well, it's telling you a whole story. It's saying there are 4 holes, each one is 10 millimeters wide, and here's the key part, their centers are all located on a perfectly round imaginary circle that's 60 millimeters across. This guarantees perfect alignment every single time. Okay, so we've learned a few letters of the alphabet. Now it's time to look at the grammar, the symbols and the rules that really give the drawing its deeper meaning and its structure. This is where we start to actually see the object take shape in our minds. 2 of the most fundamental symbols you're going to see everywhere are for diameter and radius. That symbol that looks like a 0 with a line through it, that always means diameter, the full width of a circle, straight across the middle. The letter R, though, that means radius, just the distance from the center to the edge. And I gotta tell you, mixing these 2 up is a classic rookie mistake that can make a part twice as big or half the size as it's supposed to be. So getting this right is crucial. And here's that translation from 2D to 3D in action. You see that simple R6 note on the flat drawing? That directly tells the machine to create this beautiful, smooth, rounded corner with a 6 millimeter radius on the final 3D part.
It's a direct command for a tool to follow a path, and you get this precise, smooth curve. It really is that direct.
So here's the million-dollar question, right? How in the world do you accurately show a complex, three-dimensional shape on a totally flat 2D piece of paper? The answer is this really clever system called orthographic projection, which lets us kind of unfold an object into multiple flat views.
Now, the two main grammars for this are called first and third angle projection. They basically just lay out the views in a different order. For example, in first angle, which is common in Europe, the top view is placed under the front view. But in third angle, which is standard in North America, the top view is placed above it. If you misread that, you could build the part backwards or upside down. That tiny symbol on the drawing is your Rosetta Stone. It's the key that tells you exactly how to read the map and build that 3D object correctly in your head.
You know, believe it or not, you've just taken your very first steps into learning this incredible language. So where do we go from here? What's the goal for this first chunk of your course?
Okay, so your mission for Module 1 is to really master these 3 key skills. You're going to go from just recognizing these abbreviations to actually using them yourself, and from just interpreting drawings to creating your own clean, accurate sketches. This is the bedrock for everything else that's going to follow.
Every amazing machine, every towering skyscraper, every single piece of technology you touch, it all started right here, with the lines, symbols, and rules you are about to master. This is where ideas get real. So, are you ready? Let's get started.